All right, so in this video, we're going to solve the first out-of-class exercise set from sections 1.1 and 1.2 for probability theory. So this is Math 311 in the fall of 21. So the first problem, 1.1-2, and this is from the 9th edition of the book. We have that, it says that all of the customers of an insurance company have at least one car insured. So that's what they start with, and that is my note down here, that all customers insure at least one, that's one or more, or greater than or equal to one car. So that means that S, our sample space, is the set of customers, all of them, and they insure at least one car. Now we're also told that 85% insure more than one car. More than one is not equal to one, it's greater than one. And so I'm going to define A as insure more than one car. Then I can say that P of A is equal to 0.85. And so I'll draw A here. And then B, we're told that the percentage of customers that insure a sports car are 23%. So I'm going to let B be the event that a customer has insured a sports car. And the probability of B is 0.23. We're then told that the number of customers, or the percentage of customers that insure more than one car and it's a sports car, is 17%. So that's an intersection of A and B. So now I'm not drawing these to scale because that would make it a lot more difficult. So I'm just going to draw A, and then our intersection, P of A and B, is equal to 0.17, right? And we know that A is 0.85 and B, the probability of B is 0.23, and we're asked for, find the probability that a randomly selected customer has exactly one car insured, and it is not a sports car. So this is find the probability that it's exactly one. So more than one is A. And everybody is at least one. At least one. So there's no zeros in there. So this is saying that we want, it's exactly one car. That's going to be the complement of A. So A complement is not greater than one car. Right? So A is greater than one car. So not A is not greater than one car, which means it's equal to exactly one car. All right? So we want not A and not B. It's not a sports car. So as soon as we know this, we now have two complements. And we either have an intersection or a union, then we know that we can use De Morgan's law. So with De Morgan's law, we're going to leave the P the same, and what we're going to do is we're going to take the complement of A complement, and that becomes A. The complement of A complement is the opposite of A complement is A. And then we flip this, that's the pattern, and then we take the complement of this, which is this. Okay? And then we have to take the complement of the whole thing. So it's A union B complement, and we want the probability of that. Well, So this is by De Morgan's law, or De Morgan's law, or however you say it. I'll apologize for pronouncing it wrong. Okay, so De Morgan's law. So this is the probability of a complement, and so this is equal to 1 minus the probability of A union B by the complement rule. Okay, and this is equal to 1 minus, now in parentheses, I'm going to use the addition rule, P of A plus P of B minus P of A and B. And we know all of those. We've been given those, actually. And so by addition rule. And now we plug in. So we've got 1 minus, and if you can either keep the parenthesis here, or you can distribute the negative sign, but be careful to change this to a positive and the other two to negative if you do that. So it may be safer for you for this higher math, right? Addition, subtraction, multiplication, division, all these simple things. Those are where we usually make the mistakes. So because of that, I'm going to leave my quantities inside the parentheses and just fill in. So I've got 0.85 plus 0.23 minus 0.17. And if I add these two together, I get greater than 1, right? So you know they have to be overlapping. So that's going to be a 1.07, no, 1.08, see, higher math, minus 17 is going to give me 0.91 inside, 1 minus 0.91 inside the parenthesis. And this is going to give me 0.09, which is the answer. So 9% of the customers insure a sports car, insure one car that's not a sports car. Exactly one car that's not a sports car. Okay. Now let's go to the second problem. Now my cat Pippi, you may be hearing her in the background. So she likes to participate in the homework solutions and videos. She's 18 and a half years old now, deaf, or almost deaf for all practical purposes. And and she knows that if she howls loud enough, long enough, she'll get what she wants. So yes, she is spoiled. But anyway, so the next problem is 1.1-6. Now we're given in the 9th edition that P of A is 0.4, P of B is 0.5, and P of A and B is 0.3. And they're asking us for, let me see, that's got to be wrong. Yep, I wrote this wrong. They want A or B here. I just wrote this wrong. This is the union of A and B. And so by the complement rule, or the addition rule, by the addition rule, P of A plus P of B minus P of A and B. Now, you don't really, when you're just asked for it directly, you just write it out. You don't have to say this is the addition rule. We know that, okay? So when you're doing a proof, kind of like up above in number 1, and we're doing several steps, we want to say what we did at each step. But if you didn't say this here, I wouldn't take off any points because we do know the addition rule. All right. So we're just going to plug in 0.4 plus 0.5 minus 0.3. So 0.9 minus 0.3 equals 0.6. I hope that was easy for you. Now, you may need to draw a little picture for the next one. Oops, that's not very clear, is it? So A and B over here. And we want A and not B. So we want the part of A that's not in B. That's just here. This part here. So let me zoom in a little bit. So if we just want this part that's in A and not in B, then we can just take A and subtract the intersection of A and B, can't we? And we know both of those. So with this aid of the Venn diagram, we can see the relationship. So this is going to be P of A minus P of A and B. So P of A is 0.4, P of B is P of A and B is 0.3, so this is going to be 0.1. And then finally, we see complements. And we see the probability of the union of two complements, so we immediately think De Morgan's law, and that's exactly what you should write next. You don't have to tell me it's De Morgan's law if you do it correctly. And so what we're going to do, you notice I add another bracket just so it's not confusing, and I'm going to take the complement of A complement, which is back to A. I'm going to flip the union and make it an intersection, and then I'm going to take the complement of B complement, which gets rid of the complement, so it's this. And then don't forget to take the complement of the whole thing. If you forget this complement, then you've got it very wrong, right? And if I were grading it, I would take off quite a few points for that, okay? So make sure that you get it right. So this is going to be a complement rule. So probability of 1 minus the probability of A and B. And that's just 1 minus 0.3 or 0.7. Okay. I hope that was easy and clear for you. This was supposed to be an easy problem. Now, this one's a clever problem. And in order for you to know how to solve this problem, you needed to do the assignment I gave you, which was to read example 1.2-2. Need info from example 1.2-2 in book. And this needs to be on your formula sheet. What it says is that for any set with n elements, okay, so for any set with n elements, the number of possible combinations of elements is 2 raised to the n power. Okay? This is very important. So, I want to work out this problem. We're going to need to think about each one of these. I've got sizes, I've got crust, and I've got toppings. Okay. So, for crust, there are 3 crusts, and we're going to choose one of them. So there are 3 choose one ways to choose one crust. So this is going to be 3 factorial over 1 factorial over 2 factorial, because 3 minus 1 is 2. Well, 2 factorial is just 2. So this is going to be 3, 2, 1 over 1 factorial is just 1. And then 2 factorial is 2 times 1. So you can do that, and that equals 3. And I think we learned that n choose 1 is n, right? We learned that. I think I gave you that. N choose 1 equals n. And n choose n minus 1 is n, right? So actually, these are equivalent. Okay. And so we have 3 sizes as well. So 3 sizes, small, medium, large, 3 crust, thin and crispy, hand-tossed, and pan. So somebody likes their Pizza Hut because that's the toppings that are the type of crust they have. All right. And so again, we have 3 sizes. We're going to choose one of them, and that's going to be 3 ways to choose the sizes. And this is 3 ways to choose a crust, or I'm sorry, one size, 1 crust. Pippi says I'm going too slow. Okay, so toppings now. I can choose all the possible ways I can choose between 0 and 12 toppings is going to be 2 to the n, which is 2 to the 12, which is equal to 4,096. Wow. Okay. So now, by the multiplication rule, the number of ways or different pizzas the number of different pizzas possible with 0 to 12 toppings is 3 choose 1 times 3 choose 1 times 2 to the 12th equals 3 times 3 times 4096 equals 36,864. Wow, that's a lot. Okay? Now, interestingly enough, I was a manager at Pizza Hut for about a year and a half, many years ago. I don't remember how many topping choices we have. Maybe it was 12. I don't know. But anyway. Now, let's do the fourth problem. This is something that just a direct mathematical proof, and I'll be honest, when I think about this, I know that there's a clever way of doing something, and I thought it was the way to do this, and I was wrong. It just leads me on a blind path, and so I had to start over. And so that first path was that I was just trying to change. I was trying to change the form of this in a clever way. And by doing that, I just made it pretty long and didn't really get to where I want to go. So we know that n choose r is equal to n factorial, r factorial on the bottom, n minus r factorial on the bottom, right? And then we know that this is equal to, and we're just going to write these two out as using this pattern that we just used. So we'll have n minus 1 factorial. We're going to have r factorial on the bottom. And then we subtract this, and I'm just going to rearrange it so that the negative 1 is at the end. This is the easiest way to see what we want to see. So n minus 1 minus r could be written n minus r minus 1 factorial. Always, when you're using factorials, you always want, if you have a subtraction of a number, you always want that to be last because it helps you be clever and see what you need to do to change this to the n minus r factorial, which is what we have over on this side, right? Okay. And then we'll write the other one, plus n minus 1 factorial over r minus 1 factorial. You can see how Pippi ramps up her crying when she gets ignored here. So I apologize. So I've got n minus 1 minus r minus 1. The minus 1s are going to cancel when we subtract. So we're going to end up with, so down here, n minus 1 minus r minus 1. Don't forget to distribute the negative sign, minus r plus 1. These cancel, we're just n minus r. Okay, so this is n minus r factorial. Now, you can probably guess that what we want to do is get a common denominator. In fact, we want this denominator and this denominator both to be equal to this denominator. So we need to use a fact that I went over a few times in class, and I hope that you easily remembered this. And that is that for n factorial, that's equal to n times n minus 1 factorial. Remember, we talked about that. Okay, so if I have n minus 1 factorial and I want to make it n factorial, I have to multiply by n. Well, if I multiply the top by n, I need to multiply the bottom of the fraction by n so that I don't change it, because n divided by n is equal to 1. So if I multiply by 1, I don't change anything, right? Okay, so that's just my notes, scribbling, just so to explain what I'm doing next. I'm not going to mess with this. I'm leaving it alone. I'm going to take this and I'm going to work on it and try to get it to equal this. Okay. So, first thing that we notice is in the denominator that we have r factorial and we have n minus r minus 1 factorial, and we want to change this to n minus r factorial so that it matches here. And n minus r factorial is equal to n minus r times n minus r minus 1 factorial, right? Because we have n minus r, and then 1 less than that is this. We have this, so we need to multiply by this to get n minus r factorial. Okay. So this is equal to r factorial n minus r times n minus r minus 1 factorial. Now on the top I have n minus 1 factorial. I need to multiply by n minus r, so that I'm multiplying by 1 here. I haven't changed this at all. R factorial is already what I wanted, so I don't need to do anything to it. And then on the other one, I have, or this is a plus, sorry. This is n minus 1 factorial on the top. Now I have r, I need to multiply r minus 1 factorial by r to make this r factorial. But when I do this, when I multiply by r on the bottom, I need to multiply by r on the top. So I need r. And then I already have n minus r factorial. So now this is equal to n minus 1 factorial times n minus r over r factorial n minus r factorial, plus n minus 1 factorial times r over r factorial n minus r factorial. Now I have equal or common denominators. So the top, well, there's not enough room there, so let's go down a little bit. So this is equal to n minus 1 factorial. I'm writing an extra step here that I wouldn't write, as you'll see in the solutions I provide, but I'll do this because I'm explaining. So n minus r plus n minus 1 factorial r all over r factorial n minus r factorial. I don't have to do that since I could just factor out, which is what I did, but this is just as good. You can do this if you like. Okay? And this was n minus 1 factorial. Make sure you get it right. So now I'm going to factor the top. And what I have on the top is n minus 1 factorial. That's in this part and in this part. I have it in both. So that's common. And when I factor it out, I'm left with n minus r plus r. And all over r factorial n minus r factorial. And then you'll notice that this cancels out, and I'm left with n times n minus 1 factorial over r factorial n minus r factorial. I just put the n in front instead of in back. And now I can easily see that's n factorial over r factorial n minus r factorial. Done. Because we started here and we go to here next, and then to here, 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 and we're back to where we started. So the way I did it in the solutions is when I got to here, n minus 1 factorial r factorial n minus r minus 1 factorial plus n minus 1 factorial over r minus 1 factorial n minus r factorial. What I did was I factored out the n minus 1 factorial from the top. And so in the first fraction, that leaves me a 1. And in the second fraction, that leaves me a 1 in the top. Now, between this and this, the biggest thing in common is r minus 1 factorial. Because remember, this is r times r minus 1 factorial. So the biggest thing I can factor out from the first term of each denominator is r minus 1 factorial. So in the first denominator, I'm left with r from this portion. And I'm left with a 1 here. Now, from the second term, between this and this, the biggest thing in common they have is n minus r minus 1 factorial. Because remember that n minus r factorial equals n minus r times n minus r minus 1 factorial. Oops. So I could factor out that. So I do n minus r minus 1 factorial. Now, I'm left with a 1 here, and I'm left with an n minus r here. Now, I have, this is 1 over r, the first fraction, and this is 1 over n minus r. So to find a common denominator here, I cross multiply, right? So I multiply n minus r up here and down here. So I multiply by 1, right? And then I multiply this second one by r in the top and r on the bottom. Okay. Let me undo my scribbling here. All right, there we go. So this is equal to n minus 1 factorial r minus 1 factorial n minus r minus 1 factorial out here. And then inside I have n minus r plus r all over r times n minus r. And again, I end up with here, this r and this cancel, so I'm left with an n on the top. So I've got n minus 1 factorial r minus 1 factorial n minus r minus 1 factorial. And then I've got n over r times n minus r. So this turns out to be exactly what I need to change each of these factorials to what I want it to be. So this is going to be n minus 1 factorial, which is n factorial. Then I'm going to have r minus 1 factorial, which is going to be r factorial. And then I have n minus r times n minus r minus 1 factorial, which is n minus r factorial, which is n choose r. So that's another way to look at this. Okay? So two different ways to think about the factoring. You choose which one you're more comfortable with. I think most of you were comfortable with the common denominator method, and that is fine. Okay? So no wrong or right way there. And that is the homework. Now, I want to go back to problem number 1. This is extra. Okay? And I had one student who was very clever, and I was very impressed with what they did. So what they did for problem number 1 again is remember that A equals ensure more than one car. B is insure sports car. Okay. And we had P of A was equal to 0.85. P of B was equal to 0.23. And P of A and B was equal to 0.17. Get back to that. So this person did a table. And I was very impressed because I don't think this is very obvious. But they said that here is A. So this was, they put A here. And this, I think this is tricky. This was more than 1. Okay? And so here would be not A, exactly 1. And then they put B here, which was sports car. And so B naught was not sports car. Okay? And so what we know here is we know that the probability of A is 0.85. That's the total. Okay? And we know that the probability of the sports car is 0.23. And we know if we add everything up, it has to be 1, right? So we were also told that A and B, the intersection is right here, 0.17. And because we have those three, we can complete this table. So we take 0.23 minus 0.17, that's what, 0.06? So yeah. And then we've got 0.77 here, 0.15 here, let's see, 9, yep. And so 15 minus 6 is going to be what, 0.09? And then higher math here, 0.85 minus 0.17. So that's going to be 15, that's 8. 7 minus 1 is 6. 0.68 here. And so 0.68 and 9 is 0.77, so that adds up. And 0.06, yeah, so everything adds up. And we wanted the probability of not A and not B, and we can just look right at the table to see it's right here. Okay? So I think this was to figure out that B was in a, let's say, if you put B in a column, you got to put A in a row. I think that's not obvious. So the person who did this, kudos to you. Great job thinking it through. And this is a legitimate solution as well. I would accept this with just this as the solution. So great job to that person. Now, number 2, I also have an alternate method. This was one that I saw. And so I think that this is probably the official proof. And this was 2B, and it said we wanted the probability of A and B naught. And so remember that we write either A or B as the union, and I'm going to say A, as the union of two disjoint sets. Okay? And so A is equal to A intersect B union A intersect B complement. How do we know this? Well, again, we're not proving it, but it's easy to see in a Venn diagram that I can break A up into two disjoint sets. Let me change my color of pen here. So here, this portion is A intersect with not B. So it's not, B is not over here. Now, let's go to purple. Not B would be everything outside of B, including what's in the part of A that's not in B. And so A intersect not B is the red. Red is, oops, wrong color. Go back to red. So the red is A and B not. Let's go to green. So then this is, the green is A and B. If I take both of these and union them, that's equal to A. And this, you notice there's no overlap. The red doesn't go into the green, and the green doesn't go into the red. So these are disjoint sets. So if I take the probability of A, that's equal to the probability of A and B union A and B not, or complement. And remember that I can, I'll use different brackets. I can group this if I like. Okay. And because I see that these are disjoint now, by the third, or by the second axiom number 2, B or 2, the probability of the union of two disjoint sets is the sum of their probabilities. Probability of A and B plus the probability of A and not B. So A and B we're told was 0.3, right? So this was 0.3. And we can see that the probability of A, okay, so that's the probability of A. All right, so then we have probability of A and B not. And probability of A was given as 0.4. Okay? So we have, so this was 0.4. So, and we are given this one, which was 0.3. So what we have is this, and so we can solve it by saying probability of A and not B is equal to, if we don't plug in values first, if we just use the symbols, that would be, we would subtract probability of A and B from both sides, and we'd get probability of A minus probability of A and B, which is 0.4 minus 0.3, which is 0.1, the same. So this is the more formal proof is starting with A as the union of two disjoint sets. All right, that's it for this homework, or actually out of class exercise. I hope the video was helpful and explanatory. If you still have questions, please feel free to come by office hours or ask me after class. We do have time after class this semester. Okay, that's it. Talk to you soon.